we are trying in Modular to create really unified compute layer for various type of heterogeneous compute. Performance grows, the productivity goes down because you need to spend more and more time. You get less and less out the percentage of the performance from the code. Suddenly, you need fast math models. Kind of became synonymous for the if you're AI. It's good.
So, welcome everyone back to the From Scratch podcast. Today, I'm really excited to be talking with Areg Melik Adamyan. He has a deep academic and industry background in compilers, systems, and network engineering, working as an associate professor at Moscow State University and leading AI compiler engineering efforts at Intel for well over a decade. He now leads the compiler engineering team over at Modular as a director, where he works on the Max AI platform and the Mojo language to unify high-performance AI tooling. Areg, thank you so much for joining us.
Thank you for inviting me. Happy to be here.
So I kind of want to start talking about like this idea of like compilers. I feel like historically, compilers have always felt like the sorcery of computer science. It's always felt like this niche that a lot of people kind of don't specialize in and work with, but people have always respected them sort of from like a distance. And so it feels like right now compilers have become significantly more central to the sort of conversation in computing and especially in AI. Could you talk a little bit about like why that kind of is the case now?
Sure. So, especially in AI, it's has a little bit of history, and as you know, the frameworks currently have kind of large kernel libraries, and AI is evolving around transformers and language models. And every time you need to do some type of innovation, you need to go to the kernel, to the library, and do something parameterize or have a different type of the graph that is now calculating something else. And that requires lots of engineering efforts and lots of manpower. So what people try to do, or they will try to generalize it, right? So they will try to bring some generality. The problem and that we encounter, as I said, that you Gen AI kind of changed the game. So you continuously have innovations around attention or other mechanism, and that have created lots of problems with this kernel fusion. So you have diversity of KV cache optimizations happening there, which requires some more new types of approaches. You have dynamic shapes, you have sparsity, quantization, custom operations. So all this is critical, and people think, oh, then we can generalize and get the compiler to do all this for ourselves, right? We parameterize, then we use the existing techniques for the compilation, which can cover to some extent. The problem is actually it's very hard to hire enough compiler engineers. Compiler engineers become very quickly become the bottleneck. Yeah? You need to have compiler engineers who um, actually know how to do the numeric stuff, because you have different types of d-types, like different types of quantization. All these things require specific knowledge in the floating point, which is hard itself. You need to know specialized hardware details. It's not everything generalizable, and you need to understand what are you targeting to get the performance. And you need to have the experience in the modeling, in AI modeling. And now you are having this, your AI research is kind of have this compiler in the loop problem, right? And this is a problem. And if you bubble up and go one level up, then in general, Gen AI inference, which itself is dynamic, touches the whole step and distributed. Problem. So you guys were talking about the fragmentation. This is another problem, because accelerators are different. Even in, like, if you take the NVIDIA as a type of accelerator, A100 is different from H100, is different from B100, and you cannot completely generalize it. And no, nothing saying that you have IMD, and now you have, I don't know, dozen of startups with various hardware, and it's very, very hard in this fragmented um, ecosystem to create performant kernels and to come up with something that will cover everything. To some extent, this is where generic programming languages and generic kernel programming languages with the compilers will come to help. As an example, of course, you know that there's a PyTorch which has a compiler component in it called inductor, just trying to solve some of these problems, and it's emitting the part that it's trained. It's emitting Triton code, right, which is covering the kernels, and for the trained and known patterns, it will create fused kernels, which are pretty performant for the targeted hardware, which usually is NVIDIA. So, what to do with the other stuff? And I think that's where like modular, that's where you guys were talking about Chris Lattner and his approach is coming in, where we are trying modular to create really unified compute layer for various type of heterogeneous compute, where library based on a library approach, where compiler will become kind of the helper tool and be in the center of this library based um, approach for AI. That way.
I definitely think like that's a great way to like cover the ecosystem in general and kind of why like compilers matter. It's definitely the case that just outside perspective looking in, there's just like a million different solutions, whether it's PyTorch and TensorFlow or even Triton. There's all sorts of approaches, all sorts of frameworks that basically are trying to do the same thing, which is just like targeting the right hardware, and everyone's just sort of making trade-offs as we go. And we'll go a lot deeper into that. But I guess before getting into that, I kind of want to talk about a little bit just how you even got into compilers initially. So, what motivated you to start getting into compiler engineering, especially given the fact that we've already established it's a little bit of a rare thing to see someone as a compiler engineer?
Oh, my own history. My own history started at university. So I graduated in Armenia in Yerevan State University, and from the very beginning, I was fascinated with the low level stuff. Sometimes you like it, sometimes you don't. I was into that. So at some point, I was rare guy who knew how to program in C, and I was recruited by small American startup who was in the electronic design automation business, and they were creating compilers for various formats, the physical design formats. So that's how I got into it. I quickly learned Lex and Yak, and then Flex and Bison, and then all the other tools. And then we added semantic processing, semantic analysis, and then we added some transformations, and voila, you have a compiler. This was way before all that we had compiler toolkit. There was no LVM. GCC was in its infancy, so there was no this type of toolkit that you can build. The only toolkit you had was Flex and Bison and Dragon Book to help you to guide through. I don't know whether you guys know about Dragon Book.
Yeah, yeah. It's funny. Our compiler professor, he made a joke about it because that was like the industry standard, and he said, "Don't worry, I'm not gonna bash you guys with the Dragon Book. We do use different textbooks now, but I have heard about the infamous Dragon Book."
Yeah, Dragon Book. I still have it somewhere there. So there's a historical artifact that's somewhere there on the shelf. Yeah, that was the first edition was the book, and that was no other book that were trying teaching you that. So we all went through that, and there was theoretical book with the AHA woman. What's it called? I don't remember what it was called. Interpreters, compilers. No, theory Theory and Practice of Syntax and Semantic Analysis, something like that. The big green book. After that, Dragon book. Yeah, so that's how I got into this area, and then I worked for various EDA companies. I was mostly involved with what is called, at the beginning was involved with what's called parser, semantic analysis, AST, that part for the Verilog, VHDL. I don't know whether you guys know about those. It's called hardware description languages. So that's was my journey, how I got into that. But then I moved to Moscow. I was dealing with some relatively similar stuff with a startup, which kind of perfected that path till the end when we were generating the layout. At the end, it became my PhD, which I defended at the Russian Academy of Sciences. And that's how Intel kind of noticed me and invited to join their ranks at Moscow. And that's how I got into that. And strangely or incidentally, I got into GCC and led the GCC team, then got into the cloud native languages Go and cloud native runtimes, then packet processing, moved to US and was involved into data platforms, machine learning, deep learning compilers, and then joined Mojo. You asked me why, what was the rationale to join Mojo, right? In the beginning. So Intel had this initiative for quite a long time, I think starting from 2019, which was called One API. I don't know whether you heard about that or not. It is practically was very similar to what Modular was doing, but was based on a programming language called SQL. The idea was to create unified heterogeneous programming environment for various accelerators, including Intel's, and to create tooling around it, to create distributed processing libraries around it, accelerating libraries like 1DNN. Eventually, it was canceled, and that's when I left Intel and joined Modular to kind of carry the torch forward. Because I think that the Modular's Max platform and Mojo is the closest we get to making that unified compute layer reality.
Yeah, and I think so this is a key topic, I think, especially there's a wonderful blog series that Chris Latner has on the Modular website. I really recommend that everybody go read it. And getting into this,
AI compute, yes.
yes, and so this idea of like unification for AI compute is such a central talking point. And so before we even get into that, could you kind of like you briefly kind of talked about it earlier, but just like give us kind of a lay of the land in terms of like how the AI compute landscape has changed, where it started with CUDA, and sort of how we've gotten to today, and why we even need unification in the first place.
So it's good. The question, but very kind of broad. So I will try to cover as much as I can, and without any promise to cover everything. So in the beginning, there was CUDA, right? So CUDA started as a GPU, general purpose graphics processing and programming, and it was intended to bring the general programming compute paradigms to the GPU. And that's how the CUDA started. It was a project from the Stanford University. I forgot its original name. Not a Rook or something. I forgot, but you guys can Google it. It was a PhD work or master's work that became PhD, which then was acquired by NVIDIA. it was basis for the CUDA. And CUDA very quickly, not quite quickly, but gradually became famous, and was at the end when you got to the deep learning and DNNs, and suddenly you need fast math models. You have perfect tool, and CUDA conquered the part and conquered that area and kind of became synonymous for the if you're AI, it's CUDA. But in the essence, it's just specific, or we can say it like low precision math models with fused kernels. Um, you were asking how did it evolve? As soon as you get burst and out this Cambrian explosion of models and usages and companies, everybody wants a pie of the CUDA's cake, right? And now you either need to replicate CUDA, which means that you can get, first of all, you will always be behind because NVIDIA owns that. Or you can get, I don't know, but I think you can get into some legal troubles because it's not open sourced and still closed, and trademarks, etc., are still there. You can go with something like OpenCL, and Chris Latner is exploring all those capabilities in his blog posts. But you're getting into this design by committee hell. Or you can actually take a step back and think what can be done there from the first principles. And that's kind of where Modular started, because in Modular not started as a programming language company. It started as let's write inference system company. So it started as, hey, Modular started with the writing kernels in assembly, in the SAS, in the NVIDIA's assembly. Then it became highly templatized C++. And you can look into, as an example, you can look into something like, for example, composable kernels is a good example of a C++ template that generate assembly. Then you can get into, for example, one DNS style DSL, domain-specific language, which in C++ that is doing generating assembly. You can now generalize and go up with Python. You could do domain-specific language in Python that is doing this. For example, Triton is an example of that type of thing. And Modular was doing that, and it get to a place when they were writing MLIR for kernels, templatized, highly parameterized MLIR for kernels. And that the next natural step was, hey, let's create another level and create a programming language on top of that. And that's how Mojo became to the birth. So Mojo was not something that started with this perfect pitch or perfect positioning. It started out of necessity. That we need to write highly parameterized, highly performant kernels for AI. And as soon as GenAI was there, it was obvious that this is a very convenient and useful tool, because you can, from one hand, you can parameterize, and from one hand, you can actually give the knobs out to the programmer for very target and device-specific optimizations. That's how we got here, and Modular open sourced 200,000, if I'm not mistaken, 250,000 lines of code for the kernels written in Mojo that shows how these things can be done.
Yeah, that makes sense. That makes sense. Yeah. I mean, I was just gonna follow up. So, why do you think, like, because I know you said matmul was like a big one, like matrix multiplication was really big reason that, like, GPUs from like NVIDIA got popular. But like, what else do you think it was? Do you think it was around the ecosystem that they built around CUDA as well, that led to like the adoption of NVIDIA essentially owning, like, what was the number, Laith? It was like 98% of like data centers are now like NVIDIA or something, right? So do you think it's because of the CUDA ecosystem that they built? And kind of how do you battle that, right? Because it almost feels like a monopoly in a sense.
Right. Okay, so let me kind of unwrap this. So there are two. So it's going from the bottom up and from the top down, right? So from the top down, you have frameworks like TensorFlow at that time, Cafe 2, and then PyTorch came out, where they're writing models, right? And then on the TensorFlow part, they were compiling it. On PyTorch side, they were doing it in eager mode for creating more and more models. So that was the research part, which was fueling the research in the models. But without hardware that can execute that fast enough so you can iterate fast in the research, it will not make sense. So, and that's where like all these, what would you say, CUDA ecosystem came handy, because you have these frameworks, then you hook into the CUDA, and now you have very fast matmos that can perfectly run. What else do you need? Practically nothing. And then model the exponential growth of models and research. PyTorch started to taking over the TensorFlow because of the faster iteration cycles, and that is driving consumption on the hardware side, which is running on CUDA because research was on CUDA, right? And then starting deploying it, which is in itself kind of self-repeating flywheel. And until recently, until AMD came out with the hardware, there were no contenders. Of course, it will become 98%. Very similar to how Intel in the CPU side, like a decade ago, was 98%. As soon as you have x86 ecosystem and you're producing better hardware, you will take the vast majority of the shares. Same was here. There was nothing else that you can run on. OpenCL was not ready. Everything else was not there. So you have CUDA hooked into the framework. Perfect combination. Now AMD is trying to battle that, and we'll see. But the problem is not that it can have better hardware. The problem is an ecosystem. Where this hardware is going to hook in, like what is going to fuel your matmul. You have a matmul on top, you have hardware on bottom, but you need some type of software so you can run it. Of course, you can run it on ROCm, and people do that. The problem is it's a kind of different parallel ecosystem. It's not the same ecosystem. We're getting to this fragmentation. You have PyTorch out of the box and all these libraries that run perfectly on CUDA. People are using that and it's running very well. On the other hand, you have something which can run with some kicks and customization and curses and etc. on AMD. And now you have, I don't know, dozens of other accelerators that now you need to have that whole ecosystem hooked into those accelerators. PyTorch, you need to teach inductor how to generate kernels. You need to port in terms of, in case of PyTorch, Triton to that backend. You need performant kernel libraries, and you need to replicate that every time for every hardware. And hardware companies, they don't have enough expertise to bring up the software quick enough. Even AMD is struggling.
So it all goes back to that first thing you said about it's an engineering problem. Like fundamentally, even those hardware companies are missing the engineers necessary to build that software stack to achieve the performance that, for example, a company like NVIDIA, who owns CUDA, could.
Well, first, you're missing engineers, and the second, bringing up practically full vertical stack is a very hard job. It's not that something you can, hey, we can do it on a weekend or on a month with 3 of us just getting together. No, it's practically a very hard job. So, and that's where we have another cornerstone of Modular, which is trying to unify that playing. Okay, saying bring whatever hardware you want. We'll give you this unified compute layer, which still has all the knobs you need to make it perform on your specific hardware, but you don't need to bring the whole hardware up, the whole hardware and whole software stack on your hardware up. And that is another compelling selling point for Modular, for us, that take us, you need to kind of do some enabling, or we can help you to do some enabling, and then you will have the whole stack running on your hardware. The perfect one API story, which Intel didn't finish.
Yeah, I want to kind of get into that as well because so working at Intel, which obviously is a massive hardware vendor, and I'm sure they were looking at NVIDIA's success and trying to figure out like, how can we break into this space? How can we take advantage? I guess at the time, Intel would have had to make a lot of decisions about where to invest their engineering efforts. So there was PyTorch and, should Intel, like, I guess for me, I'm really curious, like what drove Intel's motivations in terms of where to focus engineering efforts? Because there is PyTorch and there is this like dispatcher that basically decides which kernels to call, whether it's like XLA backend or CUDA backend or whatever. Intel could just focus their engineering efforts and plug into the PyTorch ecosystem, or they could focus and plug into the TensorFlow ecosystem. And then you ended up working on Triton and integrating that the XPU backend for that. So, what was Intel's thinking at the time? What were they thinking, and why didn't they, or I guess what motivated them to get into like the one API stuff that you were talking about, and why didn't that work out?
Okay, I can speak for all Intel and not anymore at Intel, so I can only speak with the parts that I understand or can kind of give my opinion, which is only my opinion. So it's not official. Because official, I don't know. You need to ask Intel. But I can tell you that so Intel is a producer and developer of the Aurora supercomputer. And Aurora supercomputer has Intel manufactured GPUs in it, which are called Pontevedra, or the commercial name is GPU Max 1550, which itself is a pretty performant GPU. So Aurora is number 2 in top 500 supercomputers run by Argonne National Labs. And that was kind of this directing and main force driving one API in some sense, because if they wanted to have something that they can move around and not be tied to GPU or manufacturer. So what was the driving force? And itself, let's be honest, kind of be honest, GPU Max 1550 is very capable GPU. The problem were in the on the manufacturing side. The problem were not in the software side. On the software side, the whole thing was brought up. It had a pretty good stack from bottom drivers up to the compilers and to the frameworks like 1DNN, which was hooked into the PyTorch for AI part. I'm talking about AI part. The classical HPC is a different story, but it was even better. But the problem was in the manufacturability. So there were some issues with the HBM, there were some issues with the whatever was there. So it was not very feasible to kind of manufacture at scale. So software stack was there. So the software group created the whole software stack. We provided the PyTorch team created the hookings through the SQL and one DNN for the eager mode. For the compilation part, we provided the XPU backend. There were drivers, so more or less all parts were there. There were no hardware to run and performance. There were successor, which was canceled. There were planned successor, which was canceled. There was not a successor, which was also canceled. So there is now Intel is planning and doing something else, something new. So the only vehicle that can run that stack now is a BattleMage consumer GPU, which you can buy, and if you can run on it pretty much the whole stack. The problem is that it's not very performant. It's consumer GPU. So the issues with Intel, in my opinion, is that they didn't have performant hardware to battle. It was not a problem of the stack, it was a problem of the hardware, and still don't have. What were they thinking? I don't know. So can't comment on that.
Yeah, I mean, that's really surprising to me, I guess, because I guess people just associate Intel as being a very strong like hardware company. So the idea of just like the software actually being like really solid and robust and ready, but the hardware like not matching it, I think that's like pretty surprising, at least to me. Um, I guess, but at the time, like what was the, I mean, so what were the compiler engineers sort of doing? You had the stack kind of like ready. Were people just working on, these projects and kind of hoping the manufacturing would kind of like take off and we'd be ready, or what was going on?
Yeah, practically that. So we were using the 1550. Actually, the funny part is that you can actually buy 1550 on eBay, and they are available. So we're using them as a kind of development vehicle and optimizing the whole stack on them, and waiting for the new generation of hardware to come up. And it was late, and then things went south for the whole Intel.
Did you guys have conversations? I mean, I guess since you guys were kind of like ahead of the curve essentially with the software stack ready, were there conversations about just doing everything kind of from scratch, like getting rid of the PyTorch, going straight to just, making our own sort of the API idea, but like how early did that idea kind of come into the picture? Um,
No, one API is not about Python. One API is a lower level unification layer. So Intel was and still is a very open source oriented company, and people might not know this, but Intel is maybe the largest contributor to the Linux kernel, open source. So open source mentality was there. Like PyTorch is the framework to use. So what you do is you provide all the lower levels to hook in directly to the PyTorch. So then you have the whole ecosystem enabled. And that was the thought, and that was the direction we were going to, but didn't pan out.
That's like pretty. I'm gonna add on to what Laith said. It's actually pretty crazy to think that like Intel was like it was a hardware problem and not a software problem. I just want to add a comment there. I think that's shocking because I think exactly what Laith said. Like perception, at least in the CS world, seems like Intel has software problems and not like hardware problems. So that's really interesting to like think about. Yeah.
Right. It's yeah, this is my opinion, of course, but can't like where is Intel GPU? Like what you can download PyTorch with the Intel backend from the pytorch.org, and you can run it on BattleMage. Is there anything else you can run on it? We can run it on a laptop. Yes. What else we can run it on? So that's the answer to your question.
I'm curious, when you guys worked on the Triton or the Intel XPU backend for the Triton, What was the motivation there in terms of just working with Triton specifically, or was it just about like we want to have like we want to be able to plug into sort of like all the popular frameworks, and Triton just happens to be like one of them?
Yeah, Triton very quickly became kind of default backend for the PyTorch in terms of the compilation, and it was open source. And whatever we can, we try not to reinvent the wheel, but plug into the existing open source projects. And that's why we started using the Triton and enabling Intel XPU backend for the Triton to be another path for the compilation in the upstream PyTorch. So at Intel, people always had this, as I already told, that this open source first mentality, that let's use whatever is there, hook in into the existing ecosystem to enable vast majority of the developers. So in terms of the hardware component, you are producing hardware and trying to commoditize the software, because that's the whole point, right? Buy our hardware and get the software anywhere it will run. So that means that you need to enable it everywhere you can, so it will run flawlessly on your hardware. And that was the case with the Intel XPU backend for Triton. Triton is the go-to compile backend. Let's enable it so PyTorch can run on Intel GPUs.
Yeah, and sort of the broader thing I think is really interesting with Triton, PyTorch, and sort of all of the AI frameworks, compiler frameworks. It's this kind of idea of like, generality and abstracting away complexity, having the ability to run on like all sorts of hardware, but then also the problem of like unlocking the hardware itself and like really being able to write deeply performant code. Um, I guess this is sort of a more general question, but how do you reconcile those trade-offs? Because you worked with Triton and you've seen sort of that ability to generalize and give people the ability to write in a DSL in Python where it's really intuitive and easy. But then at the same time, right, uh, all good compilers, can do great work, but there's still these performance trade-offs that are really severe. How do you, make sense of that?
You accept. So what you do is that if you need, Phil Tiller, who is the creator of the Triton, has a very good talk on PyTorch conference about these curves of the performance versus productivity. So if you need extreme performance, you need to go as lower as you can. So use assembly level, for example, SAS in case of NVIDIA, and you will get the extreme performant kernel or code for your particular use case. But the productivity goes down. So as the performance grows, the productivity goes down because you need to spend more and more time to get less and less percentage of the performance from the code. On the other hand, you have very high level programming like C++, where it's lots of trade-offs. You will get very quickly to some performance level, and then compiler kind of will be the obstacle because you cannot get past it. You need to now go into assembly. In the middle, you have the domain-specific language, something like Triton, which says practically takes the CUDA and says, hey, instead of this two-dimensional thing, we're now going into this one-dimensional assembly line thing. So you need to think into that terms, and you will get 80% of the performance with 20% of the SAS code efforts. And that is good enough for researchers, for fast experimentation, for this quick iteration of the models and research. And as soon as you get your research done, that's when you can actually think, okay, I got some type of performance, which is 80% or whatever percent is there. Do we need to spend more effort to get the rest of it? And if you need to rewrite it into the lower level thing and get it done. And this is one of the things that actually are very carefully being considered in Mojo, that this parameterization and knobs and drivers you can in the language kind of up level to the programmer that you can get better performance compared to the traditional DSLs, but in the compiler.
Yeah, and yeah, like that kind of like design principle is really interesting because you were saying like Modular kind of worked sort of from first principles and like worked their way up. So in your opinion, like what is the core target like audience of, Modular? Like who are they really like trying to make the Mojo language for? Is the idea here that we've sort of seen the complexity of the field and we want to make sure that the 80% of people are getting like the large benefits of being able to program in something that is akin to like Python but then still very performant, but it might not necessarily be as performant as, let's say, CUDA code that's just fine-tuned to the specific hardware that NVIDIA has just released. Is that kind of the idea, is picking your audience and just like sticking with it?
Well, first of all, Mojo is a very young language, so it's evolving. It's not done yet, and it's very far for being done. Second, if you ask different people in the different parts of the modular, you can get different answers. But I think that the most important is that Chris Lattner, as a creator of the language, is very specifically and concretely told that no, we are not going after the compromise. We want to get 100% of the performance, and we are targeting as much of he's talking about 100%. I would say as much as we can. 99 is also good. Performance with these abilities to parameterize and give you having the low level control over the parameterized code. So who are we targeting? I think in the long term, like, I don't know, 5 years, maybe 10 years, I don't know. We want to be generic systems programming language of choice for unified heterogeneous programming. That's kind of the grand vision and North Star. And we're step by step, year by year, going towards that goal. Currently, Mojo is mostly used for writing performant heterogeneous kernels. And in the open source library, you can see examples of those kernels that can simultaneously target both NVIDIA and AMD with some parameter tweaks. And that is a good start. Also, it has generic programming capabilities, which are also, you can see in the these open source libraries. So step by step, it's going towards that North Star, and I'm sure we'll get there. And I don't know what will happen. Everyone else will die. No, but that's what.
Yeah, die's pretty extreme, but we back
No,
that.
no, there is a
We
yeah.
believe it
We
too.
will be one of those languages. Like we will be. I would like Mojo and Max to be kind of this language of choice when you hook in, like when you open your laptop and say, "Oh, I want to do something crazy," or "I want just to run some model. I want to customize some model." You automatically do pip install Mojo and go from there. So that will be awesome, and we'll get there.
That makes sense. One thing I wanted to kind of like ask as a follow up is like you were saying like the long term ambition for a language like that is like 100% performance. So that kind of means it's inevitable that you have to work with the hardware vendors, right? Like you cannot just like take guesses on the abstractions and like handle all the stuff that's required at the bare metal. So like in order to achieve that goal, essentially you guys will have to work with all those hardware vendors, but in a sense isn't that a bottleneck, right? What if all the hardware vendors like don't want to work with y'all? But maybe like that's from an outside perspective, kind of like asking it, right? Like what if Intel says no, hypothetically, right? Like we don't want to work with you.
Intel won't work for us.
Yeah,
But
yeah.
we will talk about Intel. Yeah. No. The we will start them by one. For example, module is not using anything like we don't have any CUDA backend in our code practically. It's kind of replacing that. So of course, we're not going to start with NVIDIA, obvious, but other hardware vendors will be interested because, as we talked, bringing up the software stack is a hard task. Now, if we can get there and give them a tool, for example, some type of hardware bring up toolkit or maybe other type of SDKs that will help them to get there fast, of course they will be interested. Who will not be interested to cut their cost of hardware, the software stack bring up 2x, for example, or 10x? So, and I think it will be a matter of time and the inertia. More hardware vendors, small hardware vendors, than big hardware, middle hardware vendors, the big hardware vendors will work with us. More it will get used, and more hardware vendors will want to work with us. So, I think we'll get there.
I'm curious, how do you guys, this is sort of a more organizational question, but okay, like there's all these stages of a compiler, and everyone's kind of working on different components. What is it like organizing that? Is it very clean? Because obviously, even the front end of a compiler, or let's say the middle end of a compiler, you kind of want to make those informed hardware decisions, pretty early on. And I guess like when you are making the decisions in terms of like how to transform the code as it goes down the layers, where do you guys make the decisions in terms of firstly how to organize people into each of the modular components? That was an unintentional joke, but the modular components of the compiler and organizing those efforts, but then also I guess where do you make the decisions in terms of where do we diverge into the specific targeting for each of the hardware? And how do you even organize all of that? People are working on the middle end, but they need to be aware of, well, we're targeting this back end eventually, and we need to make well-informed decisions so that the compiler can be performant. How does that work from a leadership perspective?
Okay, so first of all, it's a startup, so everybody works on everything. But the idea is that yeah, the Max platform has a compiler team which has both the front end part, which works on the language parser and semantic analysis and intermediate part. Then there are layers of intermediate code, and there is a backend which is a code gen. So that's the compiler, the Mojo compiler team, how it is organized. On top of that, you have a graph compiler which uses the model graph representation, operation representation, does fusion, layout transformation, and it's the code that goes into the module compiler. There's a library team which provides building blocks and high performance kernels. And there's a tooling team which does debugging, profiling, all the related stuff. So that's kind of the four main parts of the organization. And there's a Gen AI team, which is the sister organization, which works on the model bring up. So how we get from the Hugging Face, weights, etc., how to rewrite it in Python, and then they fit the requirements of what is needed to be done in terms of missing operations. There is no like rocket science in this. It's just good old work. And the other part is the mammoth, which is the serving part. So practically after the GenAI brought the model, we have the model in our builds.modular.com. Now you can take the model and serve it in a container, and you can use them to go into the cloud to serve it on a scale. So that's how generically is organized modular. So no rocket science, pretty clean separation of concerns, people working together, common requirements, common goals, then splitting the work, and everybody does its part, and then integration, and it goes into the model.
And yeah, so I guess with the sort of the clean separation of concerns, how is the, I guess, the orchestration process in terms of just like, let's say people are working on the back end. Is there ever a situation where, maybe new startup that you guys are like targeting or working for, is coming into the picture where you guys have, has it been the case that the design is kind of like held up very well, where like, oh, we know that, towards this stage in the back end, this is like a great point to start targeting specific backends, or do we need to start maybe peeling it back a little bit and maybe moving that earlier in the pipeline? I guess like how clean is that design principle, and how often are you guys finding it that you guys have to re-engineer things, or maybe just like, change the abstraction levels as you go down the compiler?
Mhm. So the fundamental principles and the fundamental engineering help very well because I don't know whether you guys know, but you should know from the videos and blog post. The project for porting um, modular platform to AMD started in January and ended up in March. So it took only 3 months to port everything from NVIDIA, or not port, add AMD backend to the NVIDIA. And it's crazy because it's you have one source and it generates one binary, and that one binary JIT compiled on different platforms to target specific code. And this was all done in 3 months. So the main principles and main design choices that was done by Chris and Tim held up, and they are good, and they proven to be kind of combat ready. Let's put it that way. Of course, devil is in details. Sometimes you need to add kernels that are missing. Sometimes numericals behave differently on AMD and NVIDIA. The precision is different. So all these things need to be taken into account. And if you ask, like, are there some shortcuts being done? Of course, something happened at the startup. There is a little bit of everything happening, but fundamentally, the ideas and the design is not changing much. Let's put it this way.
Cool, yeah. So we also wanted to kind of ask a question about like debugging workloads. We think that's like super, super interesting. So, currently today, like when developers are debugging AI workloads, they're typically stuck using like traditional debuggers like LLDB or CUDA GDB. And those tools were designed for like C and C++, and they're generally good at stepping through like assembly instructions and memory state, but don't really map to the world of compilers like for AI. So like in the world of AI, and you've kind of talked about it, is like you're dealing with fused kernels, dynamic shapes, tensor layouts, graph rewrites, kind of abstractions that don't show up meaningfully in like a classic debugger. So like if we wanted to imagine like an equivalent GDB for like AI compilers, what would that actually look like? Like what would it mean to single step through like a fused kernel, or set a breakpoint at a level in like the graph or something?
Yeah. Luckily, there is a project ongoing, so sometime in the future we will come up and actually show that debugger to the world how we think it should be. Yeah, but it will be good to have, ideally, targeting someone like AI researcher that can start up with something on a very Pythonic level, and then for me the ideal debugger, but we need to ask AI researchers too. For me, ideal debugger is that you can go into the start from the Python code, go into the operations, and every time you wanted to get into the lower level, you have that ability. Oh, I built the graph. Now can I go into the graph? Okay, this is the operation. What this operation looks like? Oh, it's a fused matmul with Relu. Okay, can I go into the Mojo code? You can get into Mojo code. Can I get into the intermediate level? I go into the middle level. I can get into the SAS level of I can go into like levels of abstraction and get into the register level and see what's happening and go back. So that will be the ideal tool. Um, we don't have that yet, but I hope that sometime in the future we will have that.
Even internally, I guess at the company, where do you think the biggest like problems kind of are to be solved? at Modular? Based on just, I mean, I know you haven't been there for the longest time, but just in terms of where are the biggest bottlenecks? Is it, the hardware vendors and being transparent about just the hardware that they have? Are people willing to kind of give you guys that assistance in terms of, let's say Intel releases a new GPU? Have they been collaborative in the process of just helping you guys come up with the work that you guys need to do? Or is it the sort of thing where it's more engineering efforts and there's more specific niche compiler specific problems that you guys are running into that are tricky?
Less niche problems, more hardware related problems. For example, there's a very good initiative at Modular to target Apple GPUs on a laptop. But because the metal is closed, it's very hard to kind of do the things right and show it, show users how it's being done. We get to the point where next release there will be very basic Apple GPU support in Mojo, but having intrinsics, for example, LLM intrinsics open sourced by Apple will help us a ton, so we can do a lot more stuff there. And this is the type of problems we're encountering, that there's some documentation missing, there's something closed source, we don't know how to, like, where is the driver being resided. For example, try to find the right driver at Intel. It's a tricky task. So that type of things being better documented, better communicated, open sourced is what we would like to see. We understand that not everything is going to be open sourced, especially for the hardwares of the custom hardwares. But I think that's where something like hardware bring up tool, if we come up with that, will help a lot, because it will create kind of clear requirements and expectations what we need from the hardware vendor to give us, so we can bring up the stack.
But there are like alternative things that you guys could do, right? Because I know, like for example, PyTorch and TensorFlow, they have like MPS like backends, right? And so in a sense, like couldn't part of like the backend that y'all build use, for example, like implementation like ideas from like PyTorch's backend, like for the Apple Silicon, right?
Yeah,
Or is it like
definitely.
you guys are trying to work directly with like the hardware vendor itself?
Yeah, that's a performance issue. Of course we can. The question will be, like, if you're targeting performance, you need low-level stuff to be open and compilable, and that's where we have some gaps. So that's, I guess that covers it.
Yeah, kind of zooming out a little bit and looking at sort of just the general landscape of how AI, like even like something like Mojo was created. I know LLVM was a big driver for a lot of the progress in compilers specifically. Um, in today's ecosystem, I mean, not just at Modular, do you think LLVM still has like a very, very important role? Because I mean, AI compilers are kind of a niche subset of compilers in general. Compilers are generally way more general purpose and do all sorts of other things, whereas AI compilers are a lot more concerned with sort of the computation graph and being able to translate that into efficient code for GPUs specifically. So, do you think that in the current ecosystem, and also I know MLIR obviously was designed with that purpose in mind. Do you think like we've evolved past like LLVM and potentially even pushing the limits of MLIR and are moving towards sort of newer frameworks? Or do you think like those two things still have their place in the ecosystem?
Oh, you mean LVM and MLR? LVM and MLR still have and will continue to have lots of place. And the like Intel and IBM, for example, they moved to LLVM not that far ago, and currently the LLVM is kind of de facto standard. If you want to create a compiler for your custom hardware, that's where you go, and that's kind of the whole idea of this initial modularization that Chris had in mind occurred. Because at that point when LLVM was starting, there was nothing, right? There were GCC with a very quirky not very well documented, but has a very good structure. And there were lots of closed source compilers, and he came up with this modularized view of the world, which quickly conquered it. And now we're doing the same with the AI. Like Modular has all the inspiration to become LLVM of AI in the future. Kind of provide that all building blocks that you can use to create your own stack, your own software in from bottom up. And what is going, if you ask me like what is going to happen in the future in terms of the where are we going, I think that this is one of these biggest innovations that's happening, the modularization and higher in the stack. People want to focus on the applications and less on the AI infrastructure. So you need standardized AI infrastructure. In the same way as LLVM kind of brought you standardized compiler infrastructure, we hope to bring standardized AI infrastructure.
And is there ways that you can solve like portability across hardware generations? Like, is that something that you guys are actively working on too? Because that seems difficult. Like especially if like a new hardware generation has a lot of different specs at the lower level. Like, how do you design around that? No matter even if you have like a unified backend, right? It's still a challenge in a sense. So I love for you to talk about that.
Yeah, I don't think there is a unified backend that will cover everything everywhere. I don't think that will happen. And that's what Mojo and Modular is doing, that we are providing a unified compute layer with enough knobs and parameterization on the top that you can target the underlying hardware in a very specific way that this hardware needs to be targeted. So this library first approach, library first based approach, is giving you that all the flexibility that you still have a unified compute layer, but you have all the parameters and tools to target the specific hardware without having this magic compiler, right? Because magic compilers are being unicorns since 1960s when Fortran tries to do automatic parallelization, and they're still trying. So we don't believe in magic compiler, but we believe in unified compute layer.
I kind of want to talk a little bit about Intel's graphics compiler. I know that that's pretty central to a lot of the compiler projects that were happening at the time. Even I think for you guys, the Triton to Intel XPU backend, that was a critical component. Could you kind of speak to some of the engineering like bottlenecks that you guys faced while using the IGC? Was it ever I'm sure it was like kind of a big discussion point in terms of whether you should be even bypassing that compiler and going maybe going straight from like Triton to GPU machine code in a more direct way, because the compiler was kind of more general purpose, right? It handled all sorts of things for graphics besides just accelerated workflows for GPUs.
Right. um, Back at Intel, we cannot bypass it. We couldn't bypass it because um, the the entry to the Intel graphics compiler is PRV. So Triton was emitting SPIR-V through the LLVM and LLVM to SPIR-V converter, but you need to feed that SPIR-V to the IGC to get the binary code. Otherwise, you couldn't. And we had very good working relationship with the IGC team, and they did lots of specific optimizations, opened up lots of intrinsics for us to target the best performance. For example, 2D block loads, block stores, all the relative parameterized stuff. They did it, and IGC over time became very, very good. I would say. Are there still problems? Of course, there are problems, but could try to bypass that.
Do you think, I guess that's like the disadvantage, and I mean, obviously the advantage for a company like Modular is that, even CUDA has become something of a bottleneck in some sense to NVIDIA because they released the new hardware and they have all of these specific operations that need to be exploited, and people might have to go down to the assembly level to actually leverage it, and they're using this old framework like CUDA and having to like kind of work through that. Is that kind of like the idea here is when you're at Intel, and even these kind of bigger companies that have these established compilers and frameworks, there's sort of this like massive bottleneck, this bottleneck of not being able to innovate and sort of cut the lines and being able to go straight to the machine. Was that sort of like an issue at Intel that you faced? And you know, how do, and I guess like generally speaking, when there is these sort of conversations, like how do you guys sort of navigate that? You guys had a good relationship with that team, so were there discussions even about, how do we, politically do this, or was that not happening?
Um, so I'm not sure I got the question. Like, do we're arguing with the teams about how to do the things? Of course, we're arguing. It's a usual working process. Um, Intel is also like evolving. I think there are lots of things going on there. It's Intel at the end of the day. What NVIDIA in terms of like could have become kind of the mode? Sure, yes. And the same way as the x86 become a mode for Intel. It's not something that you can bypass. And when it grows, you have this. Now, Intel's in hardware, all the decisions are being made with the backward compatibility in mind. And that is a big thing. And that, in some sense, is problematic. In some sense, it's freeing because you don't need to make too many decisions. And I think that CUDA is getting to that point to some extent too. But on the other extent, NVIDIA itself is fragmenting its own ecosystem enough so it doesn't matter. So you have multiple layers and multiple verticals, and you can pick and choose whatever you want depending on your application. And that type of fragmentation gives them more flexibility to target the application developers, because you can choose on the top Python and on the bottom CUDA 11, and there's a path to get there. And for them, I think that they're doing it intentionally. It doesn't matter what path you choose in this fragmented ecosystem. If you're running on NVIDIA hardware, you're still running CUDA, and that's the answer. So how they are going to evolve? I think that at some point they are going to fragment their own hardware ecosystem much more than they are doing it now. Can they do it fast enough? I don't know, but that will be very challenging because you install CUDA drivers, like 13 came out, right? And you need to support everything up to, I don't know, 1080. Well, 1080 is deprecated now, I don't know. But you have this whole generational thing that needs to be supported, and that creates lots of engineering technical debt that needs to be addressed. In the same way as it's being addressed in Intel systems software with x86 in mind. Windows still can run SimCity with that bug, right?
How do you guys prevent Mojo when you guys have scaled large enough from fragmenting in the same way that NVIDIA and the other ones have?
Oh, we are not there yet. So I will be happy to address that question as soon as we get 20 million programmers. Absolutely. I'm guys going to hold you accountable for giving us 20 million programmers.
Yeah.
Your podcast and answer that question.
That's fair. That's fair. I guess if you had to give the like the quick sales pitch for someone who might not be familiar with Mojo and what you've been working on the Max platform, why do you think people should, or why do you think people in general are going to start preferring or moving to the modular stack over the well established bread and butter of PyTorch and just hardware vendors plugging into the back end? Why do you think over time people will want to move to Mojo and Modular? What do you think is the competitive edge that you guys have?
Competitive edge that we have. I think that the most important stuff that can give is that, hey, if you want to fire up a laptop, have a programming environment which is light enough and feels like Python, but will give you C++ performance quality on any GPU, and you can start with your laptop and then move to any data center GPU. That's the most important thing that I think will sell it.
Just generally making hardware accessible, right? It's like not
Yes,
everyone can get their hands on like a NVIDIA GPU, like H100s, right?
Yeah, and imagine that you can fire up a laptop, write a code on your local laptop with your NVIDIA, and they say, oh, but I want to run this now on the NVIDIA cloud, and just from your Vim or whatever IDE you're using, the API call which makes it happen. And but what about AMD? And there's just another API call which makes it happen, and everything from your laptop. And then you can say, but I want to compile, and you just download Max platform. Sorry, I was serve. You download Max platform, you instantly got your container, and you can, through Max platform, you can hook it into any cloud and start serving, and you have endpoints, and everything is transparent, easy to get, easy to use, and accessible. I think that should be amazing. There's nothing on the market currently in doing that.
How much of Modular's focus is also on the more general purpose use cases of, a programming language, not just AI workflows, but just, I want to, make a backend web server with Mojo, for example.
Backend web server, eventually, definitely. So it will come. We are startup, so we are focused on the immediate thing that will help us to kind of create revenue, pay our checks, but eventually we have great appetites of becoming more and more generic. And if you download Mojo, you can see that it's not limited to the kernels. You can do practically anything you want. There are some gaps missing in terms of the library functions, but please file issues on GitHub, and we will try to fix them as soon as we can to make it even more generic than now. So aspirations are big. Yes, we want to run all the web servers in the world in the data center.
Yeah, I mean, Laith's question is great because I would imagine like you can start like writing super performant backends with Mojo as well. Like that would be kind of the next step, right? But it makes sense right now. Like Gen AI is like the wave that like venture capital is like staring at, But eventually, like, it's like you said, it would make sense if like you're writing performant code for like all these like data centers and stuff that have a bunch of CPUs. So.
Yeah, and also just from a design perspective, I mean, it makes sense. I mean, you guys have to steer in a direction, and I know Chris kind of describes it as like Mojo is trying to be a superset of Python. So, I guess like what does that mean? Like from the day-to-day of someone who works at the company, like being a superset of Python, yes, but then also trying to compete with CUDA and making AMD and other hardware more accessible and performant. It seems like there's a lot of stuff in that as well.
Yeah. So when we talk about the superset of Python, we don't mean to kind of replace Python. No, that's not the intention. That's not the goal. That's not even in our mind. So what we think about is that there are Pythonic languages, and there are many of them. In this family of languages, we want to kind of have the ability to feel like Python, to give you the ease of Python in terms of this lightweightness, but give you the ability to target much more performant cases when needed, and be we'll say C++ for Python. Let's put it that way. So in that case, it's a superset because it can be Python, but when you need it, you can add these traits and characteristics and structures and language constructs, which will make it very performant like C++. And that is what we meant by superset. So ideally, yeah, at some time in the future, there should be a clear path that you can start writing very Pythonic code just to experiment and get it done. And then you specialize it using the language constructs and get extremely powerful and extremely performant code, which is C++ grade, all in the same language.
Kind of a fun question. I don't know how much development you do these days, but do you, how transformative do you think LLMs have been in the development of, let's say, compilers? Obviously, systems programming is arguably some of the most difficult programming that people can be doing, these days. Do you think that even a company like Modular has seen significant productivity gains from the development of LLMs?
Um, on the productivity, I think jury's still out. We are using LLMs in our day-to-day work, of course. It helps a lot, especially with the boilerplate code. It's a very useful tool. Um, there's no doubt in that. How transformative in terms of the innovation, I don't know yet, because to some extent it's a matter of statistics. Like you have large corpus of code which is not systems programming, and of course, LLM will give you better results on that than, for example, MLIR, which may be, I don't know, 100 people programming on it in the whole world. So are LLMs useful tool? Extremely useful. How they are going to contribute to the future innovations? Can't tell you now.
Maybe a more silly question, but do you think do you think that the ultimate convergence of like compilers is going to converge to an LLM just being given code in Python and then translating it to efficiently optimized machine code? Do you think that is the the final like stage of compilers?
Not necessarily. I think that front ends can be replaced because you use all these parts of this front end part to prescribe what to do. On the other hand, nothing prevents you to prescribe that in a plain English, right? And then you need some type of transformations into some new type of intermediate language from where the traditional compiler passes will take over. So I think that is realistic, and at some point, I think we will see some of these things. Um, so I'm more optimistic and hopeful that we will see the front end first, where this interaction part will take precedence. Then on the back end, because you still want your compiler to be 100% correct. You don't want it to be statistically 99% correct. So 99% correct machine code is not helpful.
Yeah, and for someone who might be looking into getting into compilers or compiler engineering, where do you think people today should be focusing? Because I think one of the interesting things, especially from what you've described, is if someone wanted to, let's say, work at Modular, there's a lot of things to learn. Like it's not just the compilers, but also that deep, sort of ML theory as well. Just knowing the algorithms and being able to understand how even the GPUs will apply. So what does it take to be a modern day compiler engineer?
Yeah, as a professor, I'm always teaching the systems programming in general. I have long answer to it. There was short, and also I have a short answer to it. Yeah, it's complicated, in short. But I think that if you're serious about getting into that, you need very basic and fundamental education in computer science, and I think I don't know whether I put it in the blog post or not. I have this program how to become systems programmer. I don't think there is a hidden something there, but it's kind of a sequence of things that you need to do. You need basic and fundamental computer science. I still big fan of structured interpretation of computer program as an introduction to the computer science, though I know that it's kind of deprecated and people don't do that anymore, because Saskin told in his lecture that people are not constructing programs anymore. They are doing exhaustive search of the library calls. So that's pretty, but again, it's not fundamental. I would like to have this fundamental introduction to the computer science through SIGP, and so you can get the abstractions right. You need data structures and algorithms, basic training. Do whatever, use whatever book you want, but just all the basics should be there. And then you need to go from the bottom up. You need to do the computer science organization design. I recommend Hennessy Patterson or Patterson Hennessy as a computer organization design. Then computer architecture, Hennessy Patterson book. Learn hardware description language, and learn. Well, you can use Harris and Harris, for example. You need to learn how to do operating systems. Go for XV6. If you guys want, I can give you the links to all this later. Learn computer link computer compiler construction, and the Cooper Corson book is very good for that. Databases, you need to know the database. The database is not how to write SQL code, but how to create database, because this is one of the fundamental missing gaps that we have in education. And then if you want to add math to have the deep learning, sure, you need to do it. And the basic algebra, basic stats will cover it. And then after that, learning deep learning is just one textbook. And you're there. It will take you only 3 years.
Yeah. I mean, it's interesting because so we've had a previous guest on, and we had a brief segment where we kind of talked about um education and how it's changing, especially with LLMs. I think there is this kind of, I think you put it nicely, like this exhaustive search over solutions, and it's actually kind of more literal when you have an LLM assisting you, and it's generally doing a search on like helping you figure out your algorithm, and then maybe it doesn't generate it right, so then you copy paste the stack trace error, and then it generates another one. And there's this kind of like funny concept of like vibe coding, where people just let the AI do the work, and then you just work between AIs to get it working. So I do think like education, especially of the coming, let's say, generations, is changing a lot, and potentially it isn't advantageous for like systems programming, where you really just have to get nitty gritty and go to the fundamentals. Um, what do you think about that? Like, how do you think people can stay grounded? But also, a lot of people will make the argument that if AI is going to stick around, it's going to be like the calculator in your, pocket. You need to be able to use it, and you need to be able to figure out how to be productive with it. How do you stay grounded?
The same way as the if you understand addition, calculator is a very helpful tool, because you don't need to use paper and pencil to add 5, 6-digit numbers, right? The same way as the AI, if you understand the fundamentals and understand the basics and understand how things are done, LLMs can be helpful. But I think that there's going to be, I think this vibe coding, this is my opinion, I think this vibe coding will end soon as people will figure out that you actually need to know your stuff. And some of the stuff will go to the LLMs, and the LLMs will become better at that stuff, but the rest of the stuff will remain in humans' possession, but the value of those humans will go up. I think that what is going to happen, my bad prediction, is that systems programmers' cost is going to increase all the time. Because try using LLM now for something MLIR specific. It will hallucinate like, I don't know. So you will need people who actually know the stuff. And the value of those people will go up eventually, which means that value of this traditional education, this long hours grinding, will go up. To some extent, I think it's very similar to the music. Like, those who understand music theory and have basic understanding can use LLMs and generative AI to write better music. And their value is higher than those who just use it for whatever they're doing now.
Yeah, that makes sense. Well, Omeed, I guess I can throw it to you potentially for one more question, but just generally speaking, where do you kind of see the future of, Mojo and Modular? I think you said it before. If you had to say like 10 years, the company's done the optimal path, and where should the company really be ideally in 10 years for you to feel like the mission has sort of been achieved?
No, the mission is not achieved. We're just in the beginning. So, um, in 10 years, yes, I would hope that Max and Modular and Mojo will become this unified compute layer of heterogeneous programming and go to programming language for anyone who wants to start heterogeneous. In 10 years, I hope that we will get covered the distributed and data center grade programming for heterogeneity. And we'll cover the web servers too. So we will become the one-stop shop for, hey, I want to do this. Let me just go to Modular. Hope to get there.
Don't worry, y'all will. And then one question I wanted to add, it's kind of a fun question too, is what has it been like working alongside Chris Latner? Because some would say he's kind of a legend in the CS community. So
Yes.
I'd love to know, like what is it like working with him? I'm guessing part of the reason you joined Modular was like you fundamentally believe that if there was someone that would lead a company like this, it would be Latner, right? So I'd love to kind of know your thoughts on just working with him, just briefly at least, because I know you've only been there for like 2-3 months. Yeah.
Yeah, it's fun. I think he always has some kind of unique viewpoints on things, which gives you some new perspective. Um, he's not afraid of targeting this big, aggressive goal of becoming a unified compute layer. And this is not something that you can see startups doing. And that was the kind of this aggressive and very ambitious goal that drove me in that, hey, these guys are unique, and this guy, Chris, is of course unique, and let me help as much as I can to make this happen. And yeah, that's one of his characteristic, that he will bring always something new to your well-defined viewpoint, and it will say, oh, okay, haven't thought about that.
Okay, well, Areg, thank you so much for coming on our podcast. We've had a lot of your time. We really, really appreciate it, and we hope the audience learned a lot about compilers, modular, and sort of the world of computing moving forward. So, thank you so much for your time.